Today we will discuss the Hilbert transform. Now, unlike the transforms that you have learnt earlier, namely the Fourier transform and the Laplace transform, which take you from, let's say, the time domain to the frequency domain, right? This transform is of a slightly different kind. It takes a time domain signal to another time domain signal, right? So, you are not changing the domains. The reason why I am discussing this before I have even started with the regular content of the communications course that is that we are going to follow in this class is because this transform is a very useful transform for representation of certain kind of signals, which we shall be most commonly dealing with, namely the representation of band pass signals, right? Since we are going to deal with band pass signals quite a lot, it is useful therefore to have this analytical tool available to us in this representation task. Later on you will find that it has a very particular, very important application in particular for the case of a certain for representing certain kinds of modulation schemes. For example, the single sideband AM modulation scheme, right? So that will be one of the major applications of this representation. So since these applications are going to come later, today we will only discuss what the Hilbert transform is all about, what it is, how it can be used for representing band pass signals in general. That is our mandate for today. Okay. To start with, let us consider what Hilbert transform is all about. Let me consider a linear filter or a linear time invariant system whose transfer function is something like this. Are you familiar with this function, signum of f? It's a very simple function. The signum of f is equal to 1 for f greater than 0 is minus 1 for f less than 0, right? So what does it look like? If this is the frequency axis or f axis, this is the function signum of f, plot of the signal function signum of f, right? It's plus 1 here. Okay, we'll define the value at 0 to be 0 itself, right? The mean value between the two extreme values. Now, with this definition of the signal function, what is the nature of the transfer function we are talking about here? Suppose I was to plot h of f as depicted here, what will it look like? Just the opposite of this, right? With this value being plus j, this value being minus j, right? Now that's a mathematical picture of this filter. Can you tell me what will this filter actually do to an input signal? How will it affect the input signal? Can you say something about the effect that such a filter will have on any input that is applied to it?
Phase difference induction.
Please speak a little loud.
Phase difference induction, that's pi by 2 phase shift.
There is going to be a phase shift of minus pi by 2 for every frequency in the input signal. Is that clear? So this filter will phase shift every frequency component present in the signal by a value of minus pi by 2, right? So that's what the Hilbert transformer does, right? It phase shifts, simply phase shifts all frequency components of the input by this amount. So if you were to look at the magnitude characteristics of this filter, what will it be? It's equal to 1 for all f, right? But this is going to be equal to minus pi by 2, okay, for f greater than 0, and since it has to be an odd symmetric function, it will be pi by 2 for f less than 0, right? So that's what a Hilbert transformer is. It's a filter which carries out a constant phase shift of minus pi by 2 radians for every frequency component that is present in the input signal.
So why are you saying it to be a minus pi by 2? It's pi by 2 for f less than 0.
You see, real signals will have both positive frequencies as well as negative frequencies. When it gets phase shifted by minus pi by 2, the corresponding negative frequency component, every real signal will have a positive frequency component and a negative frequency component, right? The positive frequency components really get phase shifted by minus pi by 2, and negative by pi by 2. But the real signal, if, so for example, if it's a cosine wave, if it is cosine omega naught t, right? What will happen to this? It will become cosine omega naught t minus pi by 2, right? Now look at the spectrum of this, right? In the positive frequencies, this will be e to the power minus j pi by 2, or the negative side will become e to the power plus j by 2. So the real phase shift is minus pi by 2, but that's only a mathematical effect of that on the imagined negative frequency components that are always present in a real valued signal. Okay, so that's something that is purely a mathematical property. Okay, now let's look at the same operation in a different way. We know that the output of any filter, see, output is something, we want to understand what is the nature of the output signal. We have said something about it, but we like to say something more about it, right? What we have said is that every frequency component gets phase shifted by minus pi by 2 radians. Can I express the waveform y of t in this case in terms of x of t? That's the next question. What is the actual waveform like for a given input waveform x of t? And I know how to find that, right? In our review of signals and systems, we learned that the output is a convolution of the input signal and the impulse response, right? So y of t is xt convolved with xt. So the question arises, what is h of t for this filter, right? So that if I know h of t, I can effect this convolution and find out what is the nature of y of t, right? So now I'll give you a small exercise to do, because this is the simple exercise in Fourier transformation. I'll also give you a hint as to how to do it, but I like you to do it yourself. Exercise is to prove that these two functions are Fourier transform pairs. Okay? Prove that j by pi t and signum of f are Fourier transform pairs. To prove this, I'll just give you a hint. Don't start with the signum function directly, because you will have a problem. It does not satisfy the Dirichlet condition directly, right? So you have a problem. It's a constant amplitude signal. It's not a finite energy signal in the frequency domain, right? It does not satisfy the Dirichlet condition. So you will have a problem in doing it directly. So do it slightly indirectly. You consider this function, which is basically, let's call this, let me define this function gf with a parameter alpha, right? And it's defined as e to the power minus alpha f for f greater than 0 and e to the power alpha f minus e to the power alpha f for f less than 0, right? Now it's okay, right? You can see that it's a signal with finite energy in the frequency domain. This is of course f, right? So first find the Fourier transform of this function or the inverse Fourier transform of this function and take the limit as alpha tends to 0, right? So if you carry out this exercise, you will be able to prove that these two functions are Fourier transform pairs. So I have more or less done the job for you. You just have to sit down and write down the equations and confirm that this is the result. Alright? Can I assume that you can do this? It will also be a good check for yourself that you can handle the Fourier transform nicely by yourself. So suppose we have this result. What does it mean? So what is the Fourier transform of inverse Fourier transform of minus j signum f? Because the impulse response is nothing but the inverse Fourier transform of the system function or the transfer function. The transfer function here is minus j signum f. Signum f inverse Fourier transform is j by pi t. So this will simply become 1 by pi t because minus j square is equal to 1. Right? So the inverse Fourier transform of minus j signum f is 1 by pi t. And therefore we can now write what y of t will be like. Incidentally, instead of calling it a general signal y of t, since it's a very special operation, I will denote this y of t by a special notation. I will call it x hat t, x cap t. This symbol is usually called a cap symbol. We will call it x cap t, and it is equal to the convolution of the actual input signal x t with the impulse response 1 by pi t, right? Which you can write, and that's the definition of the Hilbert transform. X hat t, which is the output of this constant pi by 2 phase shift filter, is related to x t through this convolution relation. And x hat t here is the Hilbert transform of xt. Are you all with me? Right? This convolution is this integral, right? X tau into h t minus tau d tau. H t minus tau here would be 1 by pi t minus tau, and that's how this integral comes. I hope it is okay. So you can view upon the Hilbert transform in two ways. One, purely as this integral, right, relating the input signal x of t to the Hilbert transform x hat t, right, or the other as an operation in which every frequency component gets phase shifted by minus pi by 2 radians. Any questions?
Why is it called a linear filter?
Why is it called a linear filter? Because it satisfies the principle of superposition, and it's only linear filters that we can express in terms of their transfer functions or their impulse response, right? So all filters that we normally deal with are linear filters, right? The superposition integral is nothing but the convolution integral. The convolution integral is basically coming out of the linearity of the filter, right? So any filter which is specified by its transfer function or by its impulse response, we are implicitly assuming it to be a linear filter. Yes, please.
Could you put HF versus F? HF is a complex function according to dimension.
In this particular case, HF is not complex. It is really imaginary only, right? You see, in general, HFF for any filter would be a complex valued function, and you will, to represent a complex valued function, typically you will have to make two plots, and a magnitude plot plotting magnitude of HFF and a phase plot, right? We can do that also here, right? In this case it happens to be purely imaginary, so one plot is good enough. If it is either purely real or purely imaginary, one plot is easy to will describe the whole thing. But if you wish, you can still go back to the two plot system, and what will be the two plots in this case? The amplitude plot transfer function will be constant equal to 1, and the phase plot angle of HF, what will this be? Minus pi by 2 for this for positive frequencies, and plus pi by 2 for negative frequencies. So this also is a description of the Hilbert transform, right? This is the magnitude plot, this is the phase plot. So the question was, how do we show the magnitude and phase plots of the Hilbert transform? This is how they look like. Okay. All right. Let's look at some interesting properties of the Hilbert transform. Just like we appreciate the properties of the Fourier transform and the Laplace transform, let's look at some simple basic interesting properties of the Hilbert transform. Let me ask you, suppose I take the Hilbert transform of x hat t, what will I get back? Without doing any mathematics, can you tell me? If I take the Hilbert transform once again of the Hilbert transform of xt, minus xt, because the total phase shift will become minus pi for every frequency component. So every frequency component goes through a phase reversal. So the result the whole signal simply becomes negative of the original signal, right? So this is very easy to prove. So I'll leave the proof. It's obvious. I hope it is obvious, right? The second one is, so Hilbert transform, the first one is the Hilbert transform of the Hilbert transform of xt is minus xt, right? So carry out the Hilbert transformation twice, you get the same signal back except for change in sign, right? Now of course let's look at some special cases. Suppose I have a very simple signal x of t equal to cosine 2 pi f naught t. What is the Hilbert transform for this? If x of t is cosine 2 pi f naught t, what is its Hilbert transform? Sine 2 pi f naught t, right? What is the Hilbert transform of sine 2 pi f naught t? Correct. So the Hilbert transform of this signal, I'll depict it like this, is minus cosine 2 pi f naught t. Of course, these are very simple signals, so you can find it obviously without going through that convolution operation. You will have to judge for yourself whether it is more beneficial to use the frequency domain relationship to find the answer, or to use the time domain relationship. In this case, it's much better to look at the frequency domain, because in the frequency domain we have a single frequency component, right? So I know what happens to the signal, right? So the Hilbert transform of sine 2 pi f naught t is this. In general, suppose I now consider it the complex sinusoid and take the Hilbert transform of that. What will that be equal to?
Minus j into minus j. Material minus j. Minus j times.
Minus j times.
This
You have to be a little careful. It will depend on the sign of f naught also, right? If we are assuming of course that f naught here is positive, but suppose f naught is negative, then it will be plus j, because you are right. So it is minus j into signum of whatever is this parameter here into e to the power j2 pi f naught t. Please convince yourself that this is correct, right? You have to take into account the sign of this exponent, right? If this exponent is positive, see, when you have a real signal, they are both positive frequency components as well as negative frequency components, right? So it makes sense to say that the positive frequency gets shifted by minus pi by 2 and the corresponding negative frequency component gets shifted by plus pi by 2 or gets multiplied by plus j and minus j, right? But when you have a complex exponential, you have only a single frequency component, either that's positive or it's negative. So whether it gets multiplied with minus j or plus j will depend on whether this is positive or whether it is negative, right? Are you with me on this, everyone? Good. Some other properties. If you have any question, please raise it. I'll try to make sure that all of you understand what I'm saying. So I can assume that it's okay, right? All right. What can we say about the energies of xt and x hat t? What is the relationship between the energy? Suppose x of t is an energy signal. Will be same. Why? Because mod of h of f is equal to 1, right? So if you look at in the frequency domain, x hat f, the Fourier transform of the Hilbert transform of xt, I'll denote by x hat f, but this is equal to minus j signum f into x of f, right? So look at the magnitude of this. This is equal to, and from Parseval's theorem we know that the energy function can be written in terms of this equality holds. So this is the same for both of them. That means the energy of xt and x hat t are the same. Similarly, if xt was a power signal rather than an energy signal, you could again check that the powers will remain the same. Alright. So the property that we have just discussed is that xt and x hat t have the same energy or power, as the case may be. Alright. Next property, and this is also quite interesting. You can almost deduce it from the case of the simple case that we discussed for the case of sine wave. What is the Hilbert transform of cosine 2 pi f naught t? Sine 2 pi f naught t. What is the relationship between these two? They are orthogonal to each other, right? In general, one can show very easily that x of t and its Hilbert transform would be two orthogonal signals. Okay, so xt and x hat t are mutually orthogonal, right? Mathematically, this is written like this. Right? Of course, this statement is for the energy signals. For the power signals, there will be a slight modification of this statement mathematically. How do we prove this? Proof. Any ideas? One way is to substitute for x of x hat t in terms of xt, the convolution integral, and see what happens to this integral. That will be rather complicated, I can assure you. Right? Is there a simpler way? If we can somehow go from the time domain integral to the frequency domain integral. And how do we do that? A slight generalization of the Parseval's theorem. Right? There is a generalized Parseval's theorem available which talks about two functions, integral of the product of two functions. I'm sure you know about it, but in case you don't, I'll just tell you that. So by Parseval's theorem, which is actually the most general form of the Parseval's theorem, this time domain integral Again, I'll leave the proof for you to work out yourself or look it up in some book. This will be equal to xf into the conjugate of the the conjugate of the Fourier transform of the second function, right? So this will become x conjugate f df. You can see that the normal Parseval's theorem is a special case of this. You can think of mod of xt square as for a real signal x square t as xt into xt, right? So when you apply the generalized Parseval's theorem on that, you will get xf into x conjugate f. In this case, you will get xf and conjugate of the Hilbert the Fourier transform of x hat t, which is x hat f, right? Okay. So as far as the proof of this is concerned, at the moment I am leaving it as an exercise for you. Please see if you can do it. If we have this, what is the value of this integral? So what we are saying is integral of xt x hat t dt is equal to integral of x hat f x hat conjugate f, sorry, xf into x hat conjugate f df, right? Let's substitute for x hat f. It is equal to x hat conjugate f is equal to j signum f, we are taking the conjugate, into x conjugate f minus j signum f becomes plus j signum f because of the conjugation operation, right? Xf becomes x conjugate f because of the conjugate operation. This is equal to x hat conjugate f. I have substituted for this, right? This is equal to j signum f into mod of xf square df, and this is equal to what is the value of this integral? Is it obviously 0? What kind of a function do you have inside the integral? It's an odd function of f. Xf mod square for a real signal is an even function, right? Magnitude square function or magnitude spectrum is an even symmetric function. Signum f is an odd symmetric function. The product would be an odd symmetric function, right? And therefore the value of this integral is 0, which proves our result. So you must judge in the case of problems in Hilbert transform whether to do the required operation in frequency domain or time domain, right? It's so easy to show this in the frequency domain, but if you were to proceed in the time domain, it will be much more involved to prove the same result, right? One last but very important property is the following. This is something slightly more involved. I'll just state the result here and again ask you to see if you can prove it, right? If not, we'll discuss it in one of the problem sessions, right? But try. Suppose you have two signals, I'll call them CT and MT, and they have what we say non-overlapping spectra. That is, in the frequency domain they don't overlap. The two time domain signals, but in the frequency domain they don't overlap. Since obviously if they are non-overlapping, one of them will contain lower frequency components, the other will contain higher frequency components, right? So without loss of generality, let MT be the low pass function, right? So we say that MT is low pass means its spectrum is in the occupies the lower frequency components, and CT is high pass in that sense, right? It could be the other way around, but we have just decided to do this. Then if you consider the Hilbert transform of the product of these two functions, these two signals, if you look at the Hilbert transform of mt into Ct, it will turn out to be nothing but mt, the same low pass signal mt, which is being used here, multiplied by the Hilbert transform of Ct. Okay. So proof of this, at the moment I am leaving that as an exercise. If necessary, we will discuss it in the tutorials, but it's something that you have to sit down and prove, right? It's not obvious, right? So therefore don't attempt to visualize it right away. You'll have to sit down and work it out. But as a consequence of this, the two special cases which are particularly relevant to us, because we deal with such situations quite commonly, is when C of t, the so-called high pass signal, happens to be what we call a carrier signal of some high frequency omega naught, right? And MT is a MT is a signal with much lower frequency band. That is, the highest frequency component in MT is smaller than omega naught, right? Then that condition will be satisfied, right? And what will happen to the Hilbert transform of this then? If you apply that result, it will become MT into the Hilbert transform of cosine omega naught t. So it will be MT sine omega naught t, right? So this is a very important special case of that. Similarly, MT sine omega naught t would be minus MT cosine omega naught t. Are you with me? So this more or less is a reasonably good introduction to the Hilbert transform definition and its properties. We will next look at the application of the Hilbert transform in representation of signals, particularly representation of band pass signals, which is what I mentioned in the beginning, that it has major applications there. Okay. To do that, if you have any questions, if you want a discussion on some concept that we discussed so far, we can take a couple of minutes before I proceed further now. I like to keep this as interactive as possible. So if you have any questions, please come up with them. No questions? So is it fair for me to assume that the concept of Hilbert transform is simple enough for you to have been totally absorbed in the at the moment? Is it okay? All right. Okay, let's look at the next concept. The next concept that I am going to introduce, based on Hilbert transform introduction that we just had, is the concept of analytic signals. Right? Okay, let's say xt is a real valued signal. Again, let me first give you a little bit of motivation. We have discussed earlier, and you have discussed at length, I am sure, in your course on signals and systems, that it's much more convenient for analysis to work with the complex representation of a sinusoid than the trigonometric representation of the sinusoid. Right? For example, instead of working with cosine omega naught t, it's much more simple to work with e to the power j omega naught t. Right? So in this case, in that sense, e to the power j omega naught t is an analytic representation of cosine omega naught t. We want to generalize this concept to arbitrary signals, any signal, not necessarily only sinusoidal signals. That is the motivation behind what I am presenting here, right? And obviously, from our analogy with the real signal, from our analogy with the sinusoidal signal, such an analytic signal must necessarily be a complex signal, right? So we need to define or introduce the concept of an analytic signal, which is obviously going to be complex and which would have a similar simplification which is offered by the normal complex exponential representation of a sine wave, right? So we introduce for a real valued signal x of t its complex analytic representation as x sub pt. We will soon come to the point as to why we have used the subscript p in a few minutes, whose real part is x of t. X pt is a complex valued signal. Its real part is the same real valued signal with which you started, but whose imaginary part, it has an imaginary part, is the Hilbert transform of xt. Okay, so that's the concept of an analytic signal. An analytic signal has this composition. You can now see that your complex exponential is a special case of this representation, isn't it? If this is cosine omega naught t, this becomes j sine omega naught t, which is e to the power j omega naught t. So that becomes a special case of this, right? And this is a more general form of that analytic representation, right? We'll see. We'll try to get used to this and try to develop a feel for this representation as to what it can do for us. Now, one of the things that we can see is, okay, before I do that, let me again discuss conceptually as to one other significance of this representation. Suppose I work with a signal like this. Okay, let's consider the signal mt cosine omega naught t. Okay, suppose I ask you a question as to, or maybe let's make it slightly more general, omega naught t plus theta, right? Suppose I ask you to visualize this signal as a waveform. It's a product of two signals. We are going to discuss this kind of product signals in detail when we discuss modulations, but this is as good a time as any other to discuss what is the nature of the signal, what does it look like. Assume that M2 is a message signal of which essentially contains low frequencies. It's a low pass signal. When I say a low pass signal, essentially it contains low frequencies, right? Much lower than, let's say, the so-called, what we typically give the name as carrier frequency omega naught, right? So let's say the highest frequency component of MT is much smaller than omega naught, right? So let me make it more. Let's say this is your message signal MT. This is what it looks like, the waveform MT, right? And the carrier looks something like this, or this cosine wave looks something like this, much higher frequency, right? So what will this product look like? Can you say something? Is it easy for you to imagine that this is what the product will look like, right? Okay, if not, let me do some manipulations. Basically, to visualize this, we have to answer one question. It's obvious that the product signal is a fluctuating signal, fluctuating at this rate. It's the same cosine wave signal, cosine omega naught t signal, with some instantaneous amplitude which is governed by the value of mt, right? Suppose I ask you the question, what is the instantaneous amplitude at time t? How will you answer that question? Is it mt or something else? Okay, let me do a slight expansion of this trigonometric identity. This is mt cosine theta cosine omega naught t minus mt sine theta sine omega naught t. So what is the instantaneous amplitude? Right? This, no, it is, if you remember, if I want to go from here to here, this always has to be a positive quantity, right? And what will this be equal to? It will be m square t cosine square theta plus m square t sine square theta. This is simple trigonometry for you, right? Simple trigonometry. Is it okay? Which, if you were to simplify, will be square root of m square t, which is how much? Well, in general, mod of mt. The sign information will be lost, and it has to be a positive function, right? So really speaking, if I write something like this, what I am saying is the instantaneous amplitude is governed by the modulus of mt, the positive value of mt. Mt itself will be going positive and negative. For example, the original signal was like this, it was going positive and negative. But if I look at this signal as, if I want to look upon this as a waveform, I can ask the question, it's a sinusoid, I know that it's a sinusoid of high frequency. To visualize it, the important question is, what is the instantaneous amplitude of that sinusoid?
So it agrees with the higher amplitude of entry, but in long run viability is saying that the amplitude is entry.
I'm talking of amplitude as against this function mt. So I'm not saying this is equal to mod of mt cosine omega naught t plus theta. But to visualize it, I'm asking, what is the amplitude of the signal at time t? The answer is the amplitude is whatever is the magnitude of mt.
So at all t I'm going to have the amplitude of entry and different.
No, amplitude has only one, see the question, you have to appreciate, amplitude has only one significance. If I say a cosine theta or minus a cosine theta, what is the amplitude? A. That's what I'm referring to. You appreciate what I'm saying now? Okay? Amplitude does not, minus, the minus sign has to be incorporated into the phase information. Is that clear? So I'm talking about the instantaneous amplitude. So if you look, so that's one way of visualizing the signal. The important reason why I brought this up here is that such a signal you can see in terms of some fine variations whose amplitude variations are dependent on the magnitude of mt, right? You can think of this, for example, this waveform as a very important attribute of this product waveform, right? And this waveform, which basically is a trace of the amplitude of the signal, this sine wave as a function of time. You can think of this a trace of the amplitude of this waveform as a function of time, right? That we call the envelope function of this such a signal. So you have actually a band pass signal here, and there is a concept which you can define here, which you can call the envelope of a signal. The envelope of the signal is a trace of the peaks of the sine wave that you are working with. The sine wave that you are working with, this, if you trace out the peaks of this, that forms the envelope of the signal, right? And it's easy to visualize this kind of an envelope when you have product of a low pass signal and a high pass signal, right? When you have a sinusoid like this multiplied by a low frequency function like m of t. You know, these are slow fluctuations. These envelope fluctuations are slow fluctuations, right? But the sine wave fluctuations are dictated by the value of omega naught, which is much larger, right? So the point that I was basically making is that for band pass signals of this kind, right? That's it. This is a band pass signal is hopefully obvious because the Fourier transform of this signal will be translated version of the Fourier transform of mt, frequency translated version, and therefore it becomes a signal which is a band pass signal. So in general, a band pass signal of this kind, you can identify an important attribute of that waveform which you can call the envelope of the waveform, and that contains some useful information about mt itself, right? In this case, it is not exactly equal to empty, it's a modulus of empty. As you can see, empty goes like this, but the envelope goes like this, right? The envelope is this, which is mod of empty. The actual signal is this, right? But the envelope, which is a trace of only the peaks of these fluctuations, is mod of empty. We will discuss this waveform in much more detail later when we discuss amplitude modulation. For the moment, my only simple point that I wanted to make was that such a signal is associated with the concept of an envelope, right? And I wanted to introduce this because actually in general, for any kind of signal, whether or not it is band pass in nature, mathematically one can define the concept of an envelope in exactly the same way that I have defined here, right? And the next concept therefore that I will take up in the next class is the concept that xpt is sometimes also called the pre-envelope of xt. Or simply the complex envelope. But before introducing this concept, I wanted you to understand what envelope means, and that's why I digressed a little bit, right? So complex envelope of x of t. So this analytic representation x sub pt, which is defined as xt plus j times x hat t, we also call the pre-envelope of xt or the complex envelope of xt. Precisely what is the relationship of this x sub pt to the envelope that we just discussed is something we will take up in the next class. Thank you very much.